Good morning. There's an 80% chance of rain on Friday at 9 a.m., says the Met Office in its weather forecast for Oxford. An 80% chance of rain. What does this mean? Well, if you have lots of days, like the coming Friday, then you expect to get it to rain for 80% of those days. That's an explanation that's useful to interpret the weather forecast and to behave accordingly. Get your umbrella out and don't get wet. Now, mathematically speaking, that's not a very good explanation, though, is it? What does it mean, lots of days? What does it mean, days like that one? After all, there's only one Friday this week about which this statement is being made. So we need something more here, particularly from a mathematical perspective. There's an 80% chance of rain. Is weather random? There's some philosophical questions here. In the real world, many things that we don't fully understand or fully observe may appear to be random, and it may be useful to use probabilistic modeling. There's an 80% chance of rain. How can the Met Office make such a statement? Is there evidence? Is there data that they've collected? Yes, there is. They've got lots of weather stations all over the country. They have devices on planes. They have weather balloons that they launch, and they get a lot of data, and they analyze the data. These are statistical questions, right? They can predict the future based on the past. It's a rather sophisticated statistical application because there is a lot of data involved, and also because predicting is harder than just describing. And about the future in particular, well, you have to use some modeling, probabilistic modeling, in order to make sense of the situation that you want to predict. Now, this particular situation about weather prediction is, of course, only one of many applications in the real world where probability features. And it's really across a whole range of different settings, some very elementary, like tossing a coin, rolling dice, and a well-shuffled hand of cards gives rise to some interesting probability questions. Others are much more sophisticated, and weather is one of them. But there's also financial markets, or genetics in many ways, sort of how are all the species related, how does the genetic evolution happen in terms of DNA that gets passed on and that changes, both on a big scale between species, but also on a small scale from your parents to yourselves. So there is a lot of randomness involved in that process, and there is scope for probabilistic modeling in each of those areas. It's some of it genuinely random, others maybe not so genuinely random, but we can still perceive it as random and make useful random models that help us take decisions ultimately. Now, I'm a mathematician, and you're studying probability in the context of mathematics or computer science, or both. Some of you with philosophy, others with statistics as well. But we are going to have to start at the beginning and really focus on the mathematical side of things. We want to answer the first questions I asked. How can we make mathematically precise statements about probability? And that is what this course is about. So we are going to introduce models in a way that is a little less fluffy than this 80% chance of rain, And we are going to write things a bit differently as a consequence. So, so what I want to do here is maybe call this motivation, and then say what I prefer is something like, well, I mean, this is, I put this in the context of Friday this week, but what we might do more generally is say, let AJ be the event of rain at 9 a.m. on day J of this term. Right? And then you can take 1 less than J less than N, where N is probably 40 or 39 if you exclude today. Right? So now I've used some language that I'll get back to, call this an event. Actually, I want to call this an event in a mathematical sense that I will explain. And then the next point is that we want to assess probabilities. Now, when data are involved, it's complicated, but at the outset, we might just say, suppose the events AJ each have probability P. Right? P being something in 0, 1, for this to make sense. Right? That's getting much closer to specifying a model, but we need to say something more here, and in order to fully specify a model, and that is some assumption about how these events are related to each other, and the simplest way of doing this is to say independently. Now, there are several questions, particularly coming from where we started with statistics, with statistics mainly. So there are several questions here. What's P? Clearly, but estimating P from data is not what we do in probability. That's left to the statistics course. And then there are questions about assumptions, notably independence, but also, is it the same probability each time? Even if you look at the weather forecast, they tell you, well, tomorrow the probability of rain is less than 5%. On Wednesday, it's 20%. On Thursday, 10%. And on Friday, it's 80%. So clearly, the Met Office suggests models where the P varies. But we have to start somewhere. And this is the kind of setting that you will see most likely in this course, with events that are independent and have the same probability. But of course, that generalizes in some way easily, but as far as the independence is concerned, not so easily. I'm using words here that I will, of course, explain in due course. The word event I will make precise as the next thing I do, pretty much. The word independent, if you haven't seen it, is coming in much later, or you can certainly use your intuitive meaning for now. Right? Once we have something like this, we can answer questions such as, what's the probability that we have rain for k days out of those n days this term? Right? And you can probably answer those with your school probability. If you've learned probability at school, that will be among the kind of questions that you may be able to answer already. But what we are doing here is putting some of the things that you learned at school on a more formal basis. And so I would always encourage you to think, how does this question relate to the course rather than just to what you know already? Because that way you pick up the formalism that may not be strictly necessary for the questions at the beginning of the course, but where you will need to be more fluent as we go along. Now, and there's a common mistake here in the word independent, that it kind of has too many letters. Okay, I think this is pendant. Okay, anyway. Right, so I've written on the board. It's my first lecture after a while. I always have to remind myself to write in large letters, and you can already see I started very large and got a little bit smaller. How is it at the back of the room? Can you see everything that I've written? Okay, thank you. If ever I get even smaller and you can't, please tell me, because that's useful feedback, useful interaction that we can have in a lecture. So please don't hold back. Now, before I continue with writing there, I've got a bit more advice here. My style of lecturing is going to be chalk and talk, as it used to be called. Here's my chalk, and I'm going to write on the board and paraphrase what I'm writing, but I'm also going to give some extra explanations. And what I'd like you to do, or recommend you to do, is to respond by something you might call ink and think. Ink, because it's a very good idea to take notes. And think, of course, because there's a little more than getting what's on the board onto your piece of paper, but the important process of getting it through your head and out at the other end is already a first way of processing. And you may well find that what you write with your own hand you feel more committed to when you are trying to fully understand it. And if you've written something that you're not quite sure about, you can leave a trace and say, oh, I want to get back to this. Right? So I really hope you can do that. Mathematics is a very active discipline. You really have to do it yourself. You can't rely on what you see in front of your eyes. So make sure you get the most out of lectures by doing something, such as taking notes if you can. If you feel you are falling behind and you can't listen very well, there are other ways that you can try, such as having printed lecture notes, or anything can be done with a tablet or a stylus. But you can annotate things usefully as well. As long as you stay active, that's the best way of making use of the lectures that we offer. Okay, so let's get started with chapter 1, events and probabilities. I think I need more pens. So the specific setting that we've had so far, let's see what generality we can put this in. So let's look at an experiment. And that word is sort of in inverted commas, because not everything you might think of as an experiment. But let's look at an experiment which has a set of outcomes. And let's call this set omega of outcomes. And let's call the outcomes little omega in capital Omega. I've seen that well, for the mathematicians among you, certainly the Introduction to University Maths lecturer put a video online where he writes out all the Greek letters and points out that some of them are more useful than others. So certainly omega, the last letter in the Greek alphabet, is something very prominent in probability. And so I'm using those letters here. So we call omega the sample space. Okay, the set of possible outcomes. So what sort of experiments might you want to have in mind? So here are two examples. So if you're tossing a coin, what are the possible outcomes? Well, quite clearly, two possible outcomes, heads and tails is what they're usually called. So let me write H and T. Second example, if we are throwing dice, and let's make this a little bit more interesting, let's throw two dice, and let's make them distinguishable, a red one and a blue one. What is the set of possible outcomes of this experiment? Well, in this case, we are observing two numbers between 1 and 6. Let's call them I and j, put them into a pair like this. And let's say we want I and j elements of 1, 2, 3, 4, 5, 6. Okay, so these are natural examples of sample spaces of some simple experiments. So once you have an experiment, we can define events, certain things happening in the experiment, and that may not only be observing a particular outcome, it may be something a little bit more interesting, and more generally, we call a subset of omega is called, well, any subset of omega is called an event. Or, well, for now. There may be some restrictions later, but not for a long time in this course. So again, for example, in the two settings where we have a sample space specified, we can look at the event that the coin comes up tails. That is an event, let's call it capital A, which is the singleton set that contains the outcome T. Or B, in the setting of throwing two dice, we observe a total of 9. That is, the sum of the two outcomes of the individual dice is equal to 9. And that corresponds to an event A as a subset of our sample space that has several members, because you can achieve 9 in 4 different ways. If the first one is a 3, second one has to be a 6. You can have 4, 5, 5, 4, or 6, 3. Okay, so this is just simple definitions and terminology that we are going to use. Now, we are talking about sets here, so it makes sense to just use the language of sets in our course here and recall some of the notation as well. So first of all, if omega is an outcome, and if this particular omega is the outcome that we observe, then we can talk about what it means that the event A occurs. So if omega is the outcome, we say that A occurs if omega is in A. Right? Quite naturally. So how can we use this terminology? Well, I've said these events are sets, so we have set operations that we can interpret in terms of events. So the first one here is the complement of an event. So the complement of A, and that is denoted by A with a superscript C generally here in our mathematics course in Oxford. Some people may put bars on top or have some other notation, but this is what I recommend you use. Now, if A is an event, A complement is an event as well, because it's also a subset of omega. In fact, it's complement within omega that we're taking. And what does it mean for a complement to occur? It means that A does not occur. Okay, now we can have union. So a union A union B occurs if A or B occur, or both. And intersection A intersection B occurs if both A and B occur. What more? A set difference A minus B we can define in terms of what we've already defined as A intersection with B complement. And we can say this event A minus B occurs if A occurs and B does not occur. Okay, so here is set notation, just what it means in terms of events occurring or not in our idea of representing experiments and outcomes in this way. So one more notion here, A and B as sets, or indeed as events in our context, we call them disjoint if A intersection B is the empty set, i.e. A and B, well, let's say if A and B cannot occur together. Okay, so that's a bit of set notation. We were on our quest of defining a probability model. So I've made sense of what it means to say let AJ be the event of rain at 9 a.m. on any particular day. I can use suitable sets to represent that. But now we assign probabilities to these events. And so that is our next general task. Now we assign a probability that we denote by P of A with a double bar. So to each event A, and that's kind of a little bit too general for a general definition, and I think in any case I'm postponing the general definition of what is required here to Friday. For today, I'd like to restrict to the simplest case that is relevant to our two examples of throwing dice and coins. So the simplest case is where omega is finite and all outcomes are equally likely. Now, outcomes are the little omegas. Events are the collections of omegas, subsets of capital omega. And so the consequence of the little omegas all being equally likely is that the probability of any event A is proportional to the number of elements. So number of elements of A, and that needs to be divided by the number of elements of omega for the simple reason that one of the outcomes has to occur. And so, so if you take A equal to omega, you want to get a 1 out of this. Right? So, so that's our simplest case of a sample space that is finite and a probability assigned that is making every outcome equally likely. So in our examples, A and B, from over there, with the coin toss to begin with, we have a sample space of size 2. We defined an event that we observed tails, which consisted of the single outcome tails. And so we can then conclude that with this definition, and certainly in a natural way anyway, the probability of observing tails from a coin toss is 1 divided by 2, 1/2. In the second example, where we have 2 dice and this set of outcomes that have a sum of 9, we have a sample space omega, where every combination of 2 numbers 1 up to 6 is possible. That makes it 36 possible combinations. And the event that we've written out explicitly clearly has 4 elements. And so in that setting, the probability of our event, did I call it A or B? Up there, it's again A. Okay. So that event has a probability of 4 divided by 36, and that is 1/9. Okay, in the second example, I mean, it's still a simple example, but you can kind of see that calculating probabilities in the setting where all outcomes are equally likely involves counting. And counting is a topic that that merits a little more discussion here in some generality. So let us start with some elementary combinatorics. Combinatorics is the mathematical discipline of counting in some sense. And you can count lots of different things. A kind of useful discussion for us today is to look at what's called permutations, or numbers of arrangements of objects. And let's start with arrangements of distinguishable objects. So they're all different. And you want to bring them into an order, arrange them in a particular order. So suppose we have n distinguishable objects. For example, the numbers 1 up to n, but some of this phrasing suggests that this is actually more general than that, and so we don't need to be any very specific here. Any n distinguishable objects feed into the following discussion. We can ask how many ways are there to order them. Okay, and a way to order them is a permutation. So, for example, you could just have them in the order 1 up to n, or you could have them in the reverse order. Right, but of course there are many other orders, and the question that's being asked here, how many are there? Okay, and in order to work that out, you can kind of start at the beginning. If you want to list them all in an arbitrary order, we can first wonder how many possibilities are there for what we put into the first position. And there are clearly n options for the first object. Okay, and once you've chosen the first object, there are n minus 1 remaining options. for the second object. Okay. And then after you've done this a few times, you can argue inductively. And notice that if you've already chosen your first m object, or say m minus 1 objects, then there will be n minus m minus 1 remaining to choose from for the mth object. Okay, and if you like this kind of generality here with the m, then that's great. But let me just write until there is only one option for the last object, or let me say the nth object. Right, the word inductively is kind of a powerful word because it kind of suggests that you can be completely rigorous about this. If at this stage you prefer to say, well, let's just put dots in between, that will still be fine, I think, in this course, certainly, whereas the mathematicians among you on the pure math side of the degree will be told that maybe dots are to be handled with great care. And we want to kind of handle dots with some care here as well. And ultimately, anything that you write with dots and is a valid argument actually probably can be written out as a proper induction, and hopefully without too much effort, but with effort that you don't want to spend every single time. Anyway, the conclusion for us here is, in all, we can put all this together to obtain the number of choices that we have here. And there's one more thought we need to have, which is, what do we do to n minus 1 down to 1? If you start at the top, after the n options, for each one of those n options, you have n minus 1 options. So altogether, for the first two positions, you have n times n minus 1 options. And the same reasoning applies inductively to say you need to multiply all of these numbers. So together there are n into n minus 1 into 2 times 1, which is n factorial permutations. Right, and let me write the word inductively here again, because writing these dots, there is something that you can make more precise. So as an example, there are 6 factorial ways to order the letters of a 6-letter word. And let me use the word Galois here, which is a famous mathematician, which among his many distinctions has the distinction that he has 6 different letters in his name, and of these 6 letters there are 3 vowels and 3 consonants. Now that, of course, is not particularly specific to this name, but leading on to my question that I'm asking in this setting, if we randomly reorder the letters, what is the probability that the vowels are all before all the consonants? Okay, I've been a little sloppy here. So here what I really should say is uniformly at random. in the sense of what I've defined up there, all outcomes being equally likely. So all rearrangements here being equally likely. Then here's the answer. How many ways are there of achieving this event of having the 3 vowels before the 3 consonants? There are 3 factorial times 3 factorial ways of first ordering the 3 vowels and then ordering the 3 consonants, and that gives us 36 arrangements. And what I've just said is of 3 vowels and then 3 consonants. Okay, so I've done some ad hoc calculations here. So let me maybe hook onto the notation a little bit better here. So if omega is the set of all arrangements and A subset of omega the set of arrangements with all vowels before all consonants, then what I've calculated is that the probability of the event A, which by definition is the number of arrangements that have all vowels before all consonants, divided by the size of our sample space, well, that ratio now is 3 factorial times 3 factorial divided by 6 factorial. And if you work it out, 36 divided by 720 is 1/20. Okay, so you can try the same with some other words. And of course, if the number of vowels is different, then you get a different answer. Okay, so this was the simplest setting in which we can ask how many arrangements are there to order objects when all the objects are indistinguishable. So let me now move on to the more general task of finding out how many arrangements there are if not all objects are indistinguishable. So arrangements when not all objects are indistinguishable. Okay, let's start with an example. So how many different arrangements are there when I give you 6 letters, not all different? So different arrangements of A, B, C, D. So the letter A is repeated. We have 3 letters A, and the other 3 are distinguishable. So does this relate back in any way to the previous problem that we've solved? We can kind of make some slight modification and say, well, I've got A, and A, but if I had 3 distinguishable varieties of A, then I'd be back to the problem that I've already solved. So if we had A1, A2, A3, B, C, D, then there would be 6 factorial arrangements or orderings. Okay, so what's different now? Well, we can kind of look at those. So let's look at some examples. For example, we can look at B A2, D, A1, A3, C. Or we could say, yes, but that's not the only way in which we can have B, A, D, A, A, C. We can kind of have different indices to the A's. And another example is B, A1, D, A2, A3, C. Right, so they correspond to the same ordering of A, B, C, D. And so the question really is, how many of those are there for each one that we write down? So so what we are asking is again something that we've already answered in some generality, because we are asking if we want to count how many words are there with A1, A2, A3 in any order, but B, D, and C in the places where they are, well, then it is 3 factorial ways of permuting the A's among themselves. Okay, so each one is one of 3 factorial different which differ only in the order of A1, A2, A3. So our original question was how many different arrangements are there? So each different arrangement appears 3 factorial times if we count all arrangements with distinguishable A's. So the 6 factorial orderings fall into groups of size 3 factorial, and we are interested, let's say, which are indistinguishable not with A1, A2, A3, obviously, but if A1 and A2 and A3 are all identified with the letter A we started with, then each group has size 3 factorial, and we want to count the number of groups. Okay, and this is six factorial divided by 3 factorial. Okay, well, that's an example of a number of objects that are not all distinguishable. So what is the generality in which we can make similar statements? So here is the generalization. So if I'm interested in the number of arrangements of the n objects, which I denote by little x1, and I'll have several little x1. Let me write it in this way. I have m1 copies of little x1, and then I have little x2 for a few times, and let's say there are m2 of those, and then I have some more, and finally the last object is xm, and no, not m, xk, and I have mk of those. Okay, if this is to give me a total of n, then n is m1 plus m2 plus etc. plus mk. So the number of arrangements of the n objects where we have m1 x1s, m2 x2s, etc., mk and k's, xk's, well, let me write. It is n factorial divided by m1 factorial, m2 factorial times etc. times mk factorial. Now, does this need proving? I suppose it does. The kind of proof that we've given to work out that there are 6 factorial orderings, and then there are 6 factorial divided by 3 factorial orderings in the indistinguishable case, and in the case where we had 3 the same, that same kind of reasoning can be extended, because now it's all about saying, let's make the x1s distinguishable, let's make the x2s distinguishable, have all extinguishable objects, then we have n factorial, that's our numerator. And now, within each of those arrangements, you can permute the x1s, you can permute the x2s, and you can permute the xk's in m1 factorial, respectively m2 factorial, respectively mk factorial ways. And so a group, therefore, consists of m1 factorial times m2 factorial up to mk factorial different arrangements of distinguishable objects. Right? So same reasoning, therefore, the number of groups is this ratio. There is one case that's particularly important, and that is the case k equal to 2. And if you haven't seen this general case, I think you have seen case k equal to 2. So the number of orderings of, say, we have v's and x's. Well, let's have such x's here. And let's suppose we have m of those and n minus m of these, consequently, is n factorial divided by m factorial into n minus m factorial, just by applying the formula over there in the special case. But you recognize this as a binomial coefficient of n choose m, and also see in this symmetric expression here, this is the same as n choose n minus m. Right? So this binomial coefficient is a special case of the calculation that we've done over there, the outcome of the calculation. So this is the binomial coefficient, which you may have denoted differently. So this is NCM in what many schools use as notation. But we very much like this way of writing the binomial coefficient, not the other way. Okay, so that binomial coefficient is something that you're familiar with, and it is useful in many ways, and not just in order to find arrangements of objects, but also to choose m of the given objects from the total of n. And you can do that with ticks and crosses, for example, to work out how many ways are there to form a football team of size m from a squad of size n, just by identifying a football team as all the players where you assign a tick, whereas the other players are assigned an X. And so counting how many ways there are to select a team is exactly the same as the number of ways to order the ticks and crosses. But I haven't got time to write that down, so I'll leave you with that to maybe think about more if you haven't put this together at this stage. Okay, so this leaves us to say, well, there is an 80% chance of rain on Friday. Well, I'll see you on Friday at 9 anyway.